In this video, we continue with chapter 7.1 about eigenvalues and eigenvectors. In the previous video, we were able to verify eigenvalues and the corresponding eigenvectors, and we saw theorem 7.1. In this video, we're going to continue to prove properties of eigenvalues and eigenvectors, and we're going to see how to use the characteristic equation to find eigenvalues and eigenvectors, and also how to do those calculations in Sympy. So let's talk about the characteristic equation, and we'll see this again. So to find an eigenvalue of a matrix A, we start with this equation, AX equals lambda X, and then we try to manipulate it and set it equal to 0. So we can say, well, AX equals lambda times the identity matrix times vector X. And then if we want to set it equal to 0, we can say, well, let's separate by moving the AX to the right side. So we've got 0 equals lambda multiplied by the identity matrix multiplied by vector X minus matrix A times X, all equals to 0. And then we can factor out X here. So we've got lambda I minus A multiplied by vector X, and this is all equal to 0. So since it's equal to 0, lambda I minus A is singular. And we know that the determinant of lambda I minus A equals 0. So this is known as the characteristic equation, and we're going to be working with it. Theorem 7.2 shows us that an eigenvalue has to be a scalar that satisfies this characteristic equation. So let's take a look. We're going to let A be a square n by n matrix, and then an eigenvalue of lambda of A is a scalar that we call lambda, such that the determinant of lambda I minus A equals 0. And the eigenvectors of A corresponding to lambda are these non-zero solutions of the equation lambda I minus A multiplied by vector X equals 0, which we also know is the null space of lambda I minus A. So remember, lambda I minus A is going to be a matrix because lambda I is a n by n matrix, and then with the lambdas on the diagonal, and then when we subtract A from that, A is also an n by n matrix. So this lambda I minus A gives us an n by n matrix, and so the eigenvectors correspond to the null space of that matrix. So let's take a look at the proof. A has an eigenvector X not equal to 0 with eigenvalue lambda if and only if AX equals lambda X, which following the calculations we did earlier leads us to 0 equals lambda X minus AX, leads us to the same as saying lambda I multiplied by vector X minus AX equals 0, leads us to lambda I minus A multiplied by vector X equals 0 here, if and only if lambda I minus A is singular, meaning its determinant is 0, and X is in the null space of lambda I minus A, because that's the only way we're going to get 0 here. So determinant of lambda I minus A equals 0, that's what's known as the characteristic equation of A. And the characteristic polynomial determinant lambda I minus A is an nth degree polynomial in lambda. So we know from the fundamental theorem of algebra that an nth degree polynomial has exactly n roots. That is, an nth degree polynomial equation has exactly n solutions. So in other words, we're always going to be able to write in this form that the determinant of lambda I minus A equals these n polynomials of lambda minus lambda 1 through lambda minus lambda n all multiplied. So essentially think about these as factors. And this is where the constants lambda 1 through lambda n are these eigenvalues of A. And note that some of the lambdas might be complex or some of the lambdas might be repeated. So you might have multiplicity 2 in a situation like this where lambda 1 equals lambda 2. The number of times the value comes up, if we have the same eigenvalue coming up multiple times, we call that the multiplicity. So let's take a look at an example. Here we're going to find the characteristic equation, the eigenvalues, and the corresponding eigenvectors of this 2 by 2 matrix A here, where the entries in the first row are 6, -3, and the entries in the second row are -2, 1. So the characteristic equation is going to be the determinant of lambda I minus A. So that's going to be, right, lambda I is going to be lambda 0, 0, lambda, and then we're going to subtract matrix A So that's how we get this matrix here that we're taking the determinant of, with the lambda minus 6 in the first entry. 0 minus -3 gives us a +3 in the first row, second entry. 0 minus -2 gives us a +2 in the second row, first entry. And then we get lambda minus 1 in the second row, second entry. And then we do the determinant. Well, that's going to be lambda minus 6 times lambda minus 1. And so that's going to be lambda squared minus 7 lambda plus 6. And then we're going to subtract the other diagonal, which is a 6. So we just get here lambda squared minus 7 lambda. You can expand it out and see the 6's cancel. And then we can factor out the lambda. So we've got now this equation over here that lambda multiplied by lambda minus 7 equals 0. So we know our solutions to that are going to be eigenvalues lambda equals 0 and lambda equals 7. So we go back to like algebra 2, the 0 product property. So you're just looking for the values to make zeros once you get your eigenvectors in these factored forms. So now for lambda equals 0, we'll call that lambda 1 right here. Then we're going to say lambda 1 minus 6 in the first position, 3 in the second position, 2 in the second row, first position, and lambda 1 minus 1 in the second row, second position, multiplied by, we're going to call the vector x1, x2 for the entries, equals 0. So we're solving for essentially the null space of this matrix. So when we plug in our 0 here, that gives us 2, -1 in the first row, 0, 0, multiplied by x1, x2 equals 0. So this is going to have solutions in terms of a free variable. So we're going to have t and 2t such that t is a real number. And so there's many infinitely possible eigenvectors. So one eigenvector corresponding to lambda 1 equals 0 is 1, 2. You could also have 2, 4. You could also have 1/2, 1. So there are infinitely many possible vectors here that might be solutions. So when you run these calculations in Sympy, sometimes you got a different eigenvector that's possible when you've got a free variable in your solution. And that's okay, because when you've got the free variable, how we've got the t here, you've got infinitely many possible solutions. And then lambda 2 equals 7. So when we plug in those values, okay, 7 minus 6 gives us the 1 here. We've got the 3. We're going to get 0, 0 in the second row when we plug these in, and then multiply these by x1 and x2. We again get real solutions here. We get -3tt for t being a free variable in R. So the eigenvectors corresponding to lambda 2 equals 7 is -3, 1, but that's just one possibility. You could have -6, 2, or anything else where you've got that same -3tt relationship. So let's take a look at what happens when we calculate in Sympy. So in Sympy, I put matrix A in here. You can see my code up here. And then when I do a dot eigenvals with parentheses, that runs the function to find the eigenvals of A. And so notice here, we've got 0, and then the :1 tells us that 0 eigenvalue has multiplicity 1. It just comes up once. And then we've got 7 :1. So that tells us 7 is our next eigenvalue, and it has multiplicity 1. We'll see if eigenvalues come out more than once, we get a different value after the colon. And then to find the eigenvectors, for short vex, in Sympy, we type a dot eigenvex with our parentheses. The parentheses just tells it to run that function, so you can just leave it empty. Then we get here, here's a 0, here's the multiplicity 1, and then here's an eigenvector. So remember, because we had a free variable, for lambda 1 equals 0, you could have had 1, 2, but you could have also had 1/2, 1 as a possibility. So here, Sympy is giving us 1/2, 1 as one of the possible vectors. And then for the second eigenvalue 7, which also has multiplicity 1, they're giving us the -3, 1 possibility. But remember, because that was a free variable, there were several possible results there. Here's another example. So we're gonna do a 3x3 matrix now. So we're gonna find the characteristic equation, the eigenvalues, and the corresponding eigenvectors of the matrix. So if we crank this out by hand, the characteristic equation is going to be the determinant of this equation where we've got on the diagonals lambda -1, lambda -5, and lambda +3. And then because we're calculating lambda I minus a, all the other entries change signs because the a is getting subtracted. And so to expand out the determinant here, you would do cofactor expansion by hand. And so you end up here with this equation after all of our cancellations. Lambda cubed minus 3 lambda squared minus 9 lambda plus 27. And then you factor this, and I'll show you later on, you can actually factor in Sympy as well. So I'll show you in the video for section 7.3 how to do these factorizations and determinants in Sympy. Then we get lambda plus 3 multiplied by lambda minus 3 squared, and that all is equal to 0. Let me just show you right now. So I'll handwrite it out. If you want to do this in Sympy, you would do factor function, acting on the determinant function, and then inside the determinant, you'd say lambda is like one of the symbols defined. So you could do t times, and then you do the identity matrix. So to get the identity matrix, you'd say I3. That gives you the 3x3 identity matrix. Minus a, you would have had to type a in there. And then that'll give you the factorization that matches just right down here. So again, I'll go over it in section 7.3, but if you want to go type this into Sympy to get this calculation out, you can do that on your own and verify it. And so now setting this equal to 0, we get eigenvalues -3 from this first equation. And then the second equation is going to give us the eigenvalue +3, but it's going to have multiplicity 2 because it's repeated, because this is a squared factorization. And so when we do our solution here, our eigenvalues are going to get put into the matrix and calculated. So when lambda 1 is -3, here's how our matrix works out. And then we multiply that by x1, x2, x3, and we get zeros here. So the solution is going to be in terms of the free variable t. So we're going to have t, and 3t. So again, there's an infinite amount of eigenvectors corresponding to this. So one possibility is 1, 1, 3, but remember, you could also have something like 2, 2, 6, or you could have 1/3, 1/3, 1. So when we run Sympy, we might get a different eigenvector because of the free variable, but it's still an equivalent. It's just a multiple of this eigenvector 1, 1, 3. And then our second eigenvalue is lambda equals 2, and that's got multiplicity 2 because it comes up twice. And so when we plug our lambda equals 3, so when we plug lambda equals 3 into the equations in the matrix here, we get this matrix here. When we multiply it by x1, x2, x3, we set that equal to 0. And so you can work through those calculations by hand to see you get 2 free variables, s and t. So then we have equations in the form s minus t, comma s, comma t. So 2 possible eigenvalues are 1, 0, 0, and 1, 0, -1, but because s and t are free variables, there's an infinite number of eigenvalues possible here. So this is just one possibility. So now let's see how we do this in Sympy. So we enter matrix A here, and then I do a dot eigenvalues function with the parentheses just left empty, and it gives me my eigenvalues here, -3, which comes up once, and +3, which has multiplicity 2. So that's why we have this 2 here in the second entry. And then a dot eigenvex function with the parentheses empty gives us the eigenvalues here. And then the eigenvectors show up. And in this case, the second eigenvectors for eigenvalue +3 are a match for what we got by hand. And then the first eigenvector, because of the free variable, instead of saying 1, 1, 3, Sympy said 1/3, 1/3, 1. These are equivalent. They're just scalar multiples of one another. All right, so in the next video, we will continue with our calculations with eigenvectors.